Okay, physics time. Physics time. We're talking today about inertia. Newton's. This is not a good color. Newton's laws of motion in general, and inertia specifically. And now it's going to be, ooh, look at that, peanut butter jelly. Funny, thanks, Alexa. Okay, that didn't work. Try again.
Peanut butter jelly time.
Okay, it did work. Just took a long time. Let's briefly, this is going to be entirely review. There's other than vector addition, which we will do. Actually, I say at the end. We'll spend most of the time on that probably. Here from physical science, so as long as you remember that, review real quick Newton's 3 laws of motion. So we're going to start with Newton's 3 laws of motion. In classical mechanics, in what we sometimes call Newtonian mechanics, state me the first. And I'm going to summarize it. You say the whole thing. I'll say the whole thing so it's on video record, and then I will write a summary, a very, very brief summary on the board. What's Newton's first law?
It's an object in motion will stay in motion.
You're thinking of the third one.
Acted upon by. An object in motion.
This is not good. Try again. Do it not so. Don't breathe in my.
It's ASMR. Then you gotta.
No, it's not. Okay. I was gonna actually just now because of that I was going to do ASMR on this, which is a joke we really used to make a lot in earth science like 5 years ago. But now that it has your germs all over it, I'm not going to do it. Correctly, at great length and creepily points out that Newton's first law of motion is an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an unbalanced force. And that's correct, and we abbreviate that as inertia. All of that boils down to inertia, which is the Latin word for sloth, or the of the 7 deadly sloth is inertia, an object's laziness. It's moving, and so it keeps moving, or it's stopped, and so it stays stopped. Second one to me. Unbalanced forces cause an acceleration in the same direction as the unbalanced forces, which we relate as F equals ma. What are the arrows? He put arrows on them. Why did he put arrows up there?
That is acceleration.
Yeah, but why? What's the arrows? Vectors. Both are vectors. And the third one, everyone's favorite, not everyone's favorite, not my favorite, but the one that people tend to remember the most in my experience. You want to say it, Alexa?
What is it?
Gravity?
For
For every action, there's an equal and opposite reaction.
Yeah. Good. For every action on an object, there's an equal and opposite reaction on the object that caused the first action. So we call that one action reaction. This is a slash in like the English language. It's not action divided by reaction and reaction. Those are Newton's 3 laws, abbreviated. We're not worried about them. We're worried about the first law today. An object in motion tends to stay in motion. An object at rest tends to stay at rest unless acted upon by an outside force. Galileo did an interesting... wait, hold on. Before I talk about Galileo, there is an excellent... This is one of my favorite pictures I've ever seen in any textbook ever on page 43. At least it's on page 43 of my book. Oh. No. It's a little... He's like... there's a rock wiggling next to him, and he's like... Scared face. Oh, the rock moved. That is... Think about it. Don't close your eyes. Over in the corner, and if my chair just starts moving, we would say on its own, that would be spooky. We would be like, oh, it is Halloween month. Oh, the school is haunted. Oh, the chair is probably moving because of a ghost. Why would we instantly attribute that to a ghost? Because we know that if the chair starts moving, there must have been, we intuitively, we almost biologically know if it changes. Be very careful, it is change in motion. Only unbalanced forces cause a change in motion. What's the chair doing right now? It's resting. That's lovely. That's beautiful, Lily. It is at rest. The chair it's not moving. Sure there are. Sure there are. Here's the chair. It has these little arms. It has these little legs. Are there forces acting on it? Yeah, of course. We know, at least we scientifically know, we can't have an intuitive understanding of this, but there is gravity acting on this chair, F sub g. If it was just this, what would we call this state specifically? Free fall. It would be in free fall. Would it be moving? Yeah. Would its motion be changing? Yes, because it would have to be, because of Newton's second law that I erased, it would have to be accelerating. If this were the case, it must be accelerating. Its motion must be changing, and Newton's second law, in the same direction as the unbalanced force. But it isn't. So what? The normal force. F sub n, the normal force. And now, add up to F sub, I don't know, total. What's the total force? What's the F net? 0. There's no net force. So will its motion change? No. And what's it doing right now? It's resting, and so its motion won't stop resting. It will stay at rest. This isn't spooky because you can see someone doing something, right? I want this to be on the video. Why not? Okay. First law tells us that if I give her a shove, I put it forever. Literally infinitely. It should just keep going forever. It won't change its motion. If it's moving, it should stay moving in a straight line at a constant speed. It doesn't even make it all the way off camera. So why? What up with that? What is that? I'm going to erase my vertical drawing here. Why? What? So Newton's wrong, obviously, right? Try again, Lily. Newton's wrong, obviously, right? No, Newton's not wrong. What's the force that we're forgetting about? So, I'm going to draw myself over here. Okay, so this is what I look like. I do have pants on though. There we go.
Not a shirt though.
and I do have a shirt on, and my shirt looks like this. No, it isn't. You racist. Okay. Anyway, so I put a net chair on the back. In fact, F sub what's called the push force. But then that force is gone. There's an unbalanced force. But then as soon as I'm done touching it, when it gets over to here, the push force is gone. That's why now that it has moved, it has a velocity. I'm going to do velocity in purple here. It has a velocity. And Newton says it should move in a straight line at a constant speed forever. Forever and ever. Ad infinitum. To infinity. Why doesn't it? F sub F, friction. An unbalanced force, opposite to motion, friction. Does that mean it instantly stops? Of course not. It means it slows down. It means its motion is changed by this much every time increment that goes on. It accelerates that much every time increment that goes on. And then once it stops, it then starts moving backwards, right? No, that would be spooky, because friction doesn't work like that. It doesn't then pulling it back towards me. It just stops it. It just slows it down to a stop. Friction does. So how can we test if I'm right? How can we test if Newton is right? What could we do to the chair? Or where could we take the chair? Or what's an experimental design we could do? Okay, that's disgusting. I wish you hadn't said that. You mean synovial fluid.
Oh, yeah.
We could get fluid. We could get some fluid that would reduce the amount of friction, and we could see how much more it would go. Okay, that's one idea. What's another idea? Yeah, cost is not an object. So let's go to outer space. Let's all of us go into microgravity. Let's get as far away from Earth as we can. We'll go into microgravity. Or we could just go into the orbit where we wouldn't have 80% of Earth's gravity, but would be in free fall. So everything's falling, and so we wouldn't have this friction component. And then I could push my chair, and it really would. It would just keep going on and on and on and on and on and on in that straight line forever. It wouldn't really, because it would start orbiting Earth. But if we were and this would be horrifying, other than the tiny bit of joy. But if everything in the universe stopped existing, except for the three of us and the chair, before the existential dread set in, we were like, oh, this is hell. Before that set in, we could give the chair a push, and it would go on in a straight line at a constant speed. Is Newton wrong then? No, it's right. It's just that we have this force. This is an excellent drawing. So Galileo. Now I was going to talk about Galileo. Galileo has this idea. This is the way Galileo expressed it. He said if there's a ramp he did not say frictionless, but if there's a ramp and you drop a ball, I tried to make these the same height. Pretend like they're the same height. And he rolls this ball from here. It will go all the way up to the other side and then back again forever. Why doesn't it? Why doesn't it actually reach the absolute top? Friction. His thought experiment was then, and this is Galileo, not Newton. His thought experiment was if I had an infinitely long ramp now, the same idea, except for now instead of this other end over here, I have this. How long will the ball go? Well, it'll never get up the other side because there is no other side. It'll go on forever. So that was the first idea of inertia, that this ball, even tells us it's something that rolls eventually stops, Galileo's thought experiment said that if we assume this will eventually get up here, if the table's smooth or whatever, however he would have imagined, this one would go on forever and ever. First idea of inertia in motion. Wow, Alexa with the hot takes about Galileo's ideas. Your book talks about how mass is not weight and mass is not volume. I'll trust you to read those things. You already know that's the case. We talked about equilibrium and net force. We didn't talk about the word equilibrium, but as it sits right now, let's draw the chair again. I'm really good at drawing chair. I'll draw myself in the chair too, just for giggles. Okay, I don't want that line, but I do want the handlebar. There we go. There we go. So the chair Mr. Kimes system. This system, what force acting on it? Forces acting on it. We're assuming it's just sitting still. Gravity is acting down, F sub g. And I made this one quite a bit longer because I am fat. And then the normal force acting up. And so we have a net force of 0. We already said F sub net equals 0. And we call this state equilibrium. And that means not, that doesn't mean, is one other way of saying that. That doesn't mean that there are no forces acting on it. It means that the forces are in equilibrium. They're equal to each other in opposite directions, so they cancel out. I hate that word, but they cancel out. They're in equilibrium. That's a much better way of describing it. We will, in not very many chapters, we'll talk about chemical equilibrium, how there's these opposing chemical forces. It's actually the sides of a chemical reaction, and they balance out. They cancel out. They reach equilibrium. And then finally, we don't talk about vector addition. And we don't really have time to spend as much time. I really like this drawing, so I kind of want to keep it up. But we'll do there's just not enough room if I keep it there. So we'll try to do our vector addition. Bye, Fatty. This whole class, my whole job is actually just like a disguise for me to be able to fish for compliments by drawing a picture of myself as fat and have people say you're not really that. And then I say, phew, finally. My job. Anyway, how do we do, so let's say now we know that forces are vector quantities and we know that they can add together. Look at this. We're going to assume those are the same length, even though I'm not very good at drawing either.
You're very good.
Thank you, Alexa. We're going to assume plus this plus this equals 0. That's easy. What about this? Yeah. So we pretty well. Now what about this one? Or like this. That's not 2. It equals 2. 1 plus sideways 1 equals 2. No, gosh dang it, I did it again. Question mark is what I'm trying to do. Question mark. We don't know. There is a way to find out, and we have to have numbers with them for it to actually work. One way we talked about is the tail to tip method, where if we add that one's tail to this one's tip, and then if we draw them to scale, and we actually measure them, and we get this, and we can draw the line between them. That was very good. And then we measure this line, and we measure, using the protractor, we measure that angle. We get this line x and this angle theta, and that's our result. Okay? But there's a better way. And the better way is that these all have a value, and they have an angle above the horizontal. And so if we say, Alexa, Captain Alexa, airline pilot, is flying at 200 kilometers per hour and a wind of 10 kilometers per hour is I'm trying to think of what verb to use. Blowing, I guess it's fine. Blowing at an angle of 38 degrees from the horizontal axis of the plane. What is her resultant? I already have that word almost there, so we'll just keep it. Resultant speed and, velocity and angle. I thought we were talking about forces. Yeah, but both forces and velocities are vectors, and so we can do this kind of problem with both. A classic example, or to me, a classic example of the force one would be we are pushing on a lawnmower at a certain angle. You know, like the lawnmower handle is angled. So what actual is being applied forward? Same. Or we could say that this little scrub is pulling up with a certain force at a certain angle, and I'm pulling this way at a certain angle. What is the resultant or the net force on the chair? You know, we could do something like that. What we do is we first break these into components, okay? So we have two quantities here, right? We have a velocity. Let's draw a diagram. We have a velocity. This is an airplane. Don't be mean to me. We have a velocity of 200 kilometers per hour. We'll say forward. It doesn't really say. The problem to it by someone who's better at this, but I'm going to try to make it clear here. And then we have, relative to the horizontal axis of the plane, which I'm horizontal axis of the plane, we have a wind blowing at 38 degrees from that horizontal axis. So let's call it, I don't know, that looks like 38 degrees to me. And it's going at 10 kilometers per hour. I still like to draw these kind of at scale. The nice thing about the trigonometric method, which is what I'm going to show you, draw them to scale. Like this one doesn't have to be literally exactly a 20th as much as this one. If you use the rhombus method that your book describes, you have to make these to scale. You have to make this one, let's say 20 centimeters, and this one 1 centimeter, and then you add them together and you can measure the angle between them. But the trigonometric method, you don't have to. So what do we have? Well, what's the as I have drawn it here, both of these have an x and a y component. Rather, this one has an x and a y component, and this one only has a y component, the way I've drawn it here. So we have a quantity 1, and we have v sub 2. And we're going to add v sub 1 plus v sub 2, and we're going to get our resultant. But it's not as easy as that. We can't just add them. We can't just add them. Right, that's step 1. Can't just add them. Step 2 is that we break each into that's actually step 1. Break into x and y components. So we have v1 sub y equals 200 kilometers per hour. How do I know it was given? What's v1 sub x? What's the component of this perfectly vertical? Nope, just this one. We're only talking about v1 here. What's the x component of this perfectly vertical v1? It's perfectly vertical, so what's the x component? There's no x component. 0. There is no x component. And then for v2 sub y and v2 sub x. Well, let's look at our little triangle here. v2 is the hypotenuse of this triangle, isn't it? We've forced it to be a right triangle. Do you see how if we just jam these two things together, they're not a right triangle? They have some other angle, whatever 90 plus 30 is, 128. We can't do trigonometry with a 128-degree triangle, or at least not as easily. So I forced this to be a right triangle. Now we can do trig with it. If I want to find the y component and the x component of v2, what's my hypotenuse? 10 kilometers per hour. So what trigonometric function am I going to use? You remember this guy? Oh, I've got to write it somewhere else. You remember this? Some old hippie caught another hippie tripping on acid. So how do I use that to this? Well, if I want to find y, which side of this triangle is y? You can't just... Is it the opposite or the adjacent? Is it the O or the ah? It's the O. The hypotenuse, which we know is 10 kilometers per hour, make sure you include units, 38 degrees. V times the of 38 degrees. And for me, where's your calculator?
I'm guessing one of these.
Well, no, just guess. No one can just guess trigonometry. Come on. No, it isn't. Okay, go get it. Yeah, it isn't, because that 3, 4, 5 to also be a 30, 60, 90 triangle, which this is not. It's 38 degrees. That's not even true, is it? Does it have to be? It isn't 3, 4, 5. Hey, come on, go get a calculator. Yeah, someone. Run out of time. So I'm going to type in my calculator. Sine 38. 6.156 kilometers per hour. And then 10 cosine 38. It's violent, and it's almost completely invisible in the video, so best of luck. 7 0. Step 1, break into x and y components. I'm going to this time. I'm going to leave my little diagram though. Why is this such a greasy marker? Look at how it's leaving behind all this orange Cheeto grease. Step 1, which is at the bottom of the board, leads us to which I'm going to put at the top. So once we've broken into x and y components, we sum the x and y components. So now we have v1x plus v2x equals sum of the x, and v1y plus v2y equals sum of the y, right? v1x we said was 0 plus 200, or sorry, wrong. The x the x component from here was 7.880 kilometers per hour equals 7.880 kilometers per hour. And then for the y's, we had 200 kilometers per hour plus 6.156 kilometers per hour equals 206.156 kilometers per hour. So I added the x components from one with the x components from the other, and my y components from one to the y components of the other. And now, step 3 is build a new resultant, is what we sometimes call it, triangle. So I use the sum of the x as my x component. Was 7.880 kilometers per hour. And this definitely isn't to scale, but my y component is 6.1 kilometers per hour. Answer, please. Do you see where I'm getting these numbers from for my new triangle? They're the sum from before. I can find this here is the sum. How do I find that? There are a couple ways. Yeah, it is. I'm sorry. And it also looks like straight Cheeto dust on the board. It also is making me really, really mad to keep using it, but I have to finish. So how do I find this? How do I find this hypotenuse of this triangle I've just built? You can use the Pythagorean theorem. You can use the Pythagorean theorem. You don't have to. There are other ways, but you can use the Pythagorean theorem. So plus b squared equals c squared. C equals the square root of a squared plus b squared. C equals, in this case, the sum, which in this case equals, do it. I would type in, this is how I would do it, 206.156 up 2 squared plus the quantity, in parentheses, 7.88 squared. And then I would raise that answer to the 0.5 power. And then I would, raise the answer to the 0.5 power. You guys know that raising something to the half power is the same as a square root, right? Yeah.
The answer, 206.307.
Okay, 206.307 kilometers per hour. And then the only thing we have to do now, step 4, is find the angle. I'm going to erase my step 1 now. Find the angle. How, given my little triangle there, how do I find the angle? Well, I can use any of the inverse trigonometric functions. So I could use sine to the minus first power functions. Sine minus opposite over hypotenuse. So I put sine 1 of the opposite 206 over hypotenuse 206. Both of those kilometers per hour. Angle theta equals. Can you do that one, please, Lily, real quick? This number. This is going to be a great big number. Is this going to be close to 90 or close to 0? Close to 90. Yeah, 90.
This is 0.999. Do I have to take the inverse of that?
Yes, inverse sine of it. You had already done it. This is 87.9 degrees. So it is the resultant velocity of Alexa's aircraft is 206.307 kilometers per hour at an angle of 87.9 degrees from the horizontal. This one was with velocity, but the same method of vector addition applies to forces. We don't have time, but if we did the one, if I said, changing colors mercifully, if I said, here's the chair from the back, if I said that the monkey was pulling with a force of, here's a monkey, and the monkey is pulling, that's a monkey. And the monkey is pulling with a force of 10.1 newtons at an angle of 14 degrees from the horizontal. And pulling with a force of 1,980,418 newtons at an angle of 4 degrees from the horizontal. We could add those together. You'd have to know that these two things are in opposite directions. There's a number of things that we have to do logically to process it. It's the same. We break them into their components, we add x and y, we build a new triangle, we get the resultant force. In this case, it would be force. The one we did on the board was velocity. In this opposite directions, we'd have a negative x component here and a positive x here, probably. We could do it the other way around, but we'd probably consider this one the positive x. Do you have questions about, but do you have questions conceptually about it? Why it works? That kind of thing? This is so the last test that we took, we did breaking them into components. We just broke them into components, just step 1. And now we do the rest of the steps. Step 2, adding the components together. Step 3, building a new triangle. And step 4, finding the solution. Questions?